Hello, Chem 1A. This is Chapter 6, Lecture Video 9, and we're going to be discussing coffee cup calorimetry in this lecture video. So, what is coffee cup calorimetry? It's more scientifically called constant pressure calorimetry because pressure is held constant in coffee cup calorimetry. Now, what's going on here is we have a coffee cup, and we have a reaction going on generally in an aqueous environment, so dissolved in water, and we're measuring the temperature change in the reaction as it occurs. The styrofoam coffee cup is used because it's a very good insulator of heat, so heat remains in the system, and we have relatively accurate measurements using styrofoam because of its insulation. So using this, we can actually measure delta H for the reaction, for a reaction within the calorimeter, because pressure is not changing, and delta H is defined as the transfer of energy under constant pressure. So that allows us to determine delta H, and we do it using Q is equal to MC delta T. So we can measure how much heat is being transferred from one place to another in this system or in this measurement technique, and that'll allow us to actually calculate delta H for a reaction if we want to. For instance, if we had 6 grams of sodium hydroxide, all right, so we have our 6 grams of sodium hydroxide dissolving in 100 grams of water, and the temperature rises from 21.6 to 37.8. Now, in this problem, we're going to use Q is equal to MC delta T. We're also going to utilize the fact that delta H is going to be pretty much equal to Q of our reaction over moles of the reaction. Now, I'm going to put reaction in quotes here because we actually don't technically have a reaction going on. It's more of a process. Because we have sodium hydroxide NaOH solid dissolving into NaOH aqueous. And so we're almost not even really having a reaction. We're actually just changing physical state for the most part. This is a physical change, not a chemical. So that's why reaction is kind of used loosely here. But this equation holds true still in this case. So I have a lot of information about water. I know the mass of water. It's 100 grams. I know the specific heat of water. It's not given in the problem, but I definitely give it to you on a test. 4.184 joules grams degrees Celsius. And I know the temperature change for water. I know the initial temperature of water was 21.6 degrees Celsius, and T final is now 37.8 degrees Celsius. So all this means is that I can calculate Q of H2O using MC delta T. Now, whatever energy the water gained or lost had to be from the process of dissolving the NaOH, because otherwise it was just water with solid NaOH put into it. If nothing happened, the temperature should have stayed the same. But since dissolving the NaOH caused a temperature change, that energy that the water in this case gained came from NaOH dissolving. So I can get Q of this process using the relationship between water and the process, which is basically they're equal but opposite, right, sign-wise. So whatever the Q for water is, that's going to be equal to negative Q of my reaction. So let's do some calculations. So I know Q of H2O is going to be equal to 100 grams times 4.184 times 37.8 degrees Celsius minus 21.6 degrees Celsius. And this will give me a Q of 6,778 joules of energy is my Q of H2O. Now what this means is that Q of my reaction must be equal to negative 6,778 joules of energy. And so now I have my Q in the numerator here Now I need moles of the reaction. Well, I know that for every 1 mole of NaOH that I dissolve, I get 1 mole of aqueous NaOH. So I can get the moles part from the 6.50 grams of NaOH. And I can go, okay, well, hey, I know the molar mass of this is effectively 40 grams of NaOH per 1 mole of NaOH. And I know that for every 1 mole of NaOH, I get 1 mole of, again, quote unquote, reaction or process occurring. This gives me 0.1625 moles of RXN. Now my last step here is I have this value now. My delta H here up top, I'm going to calculate up here, is equal to my negative 6,778 joules divided by 0.1625 moles. This gives me negative 41,711 joules. We need to round this to 4 sig figs per mole. Also, it was, I think, generally we'd ask for this problem in kilojoules, so let's convert that there too. So this is going to give me negative 41.71 kilojoules per mole. All right, cool. So let's do another example. Okay, a student wants to determine the delta H of a reaction. In this case, it is a reaction. It's a reaction between perchloric acid and NaOH. The student mixes 25 milliliters, and this is going to be an important value here, of a 0.5 molar perchloric acid solution with 25 milliliters of a highly concentrated NaOH solution. What the problem is just trying to say is that our NaOH is in excess, because stoichiometry is going to be involved in this problem. Both solutions were initially at 23.5 degrees Celsius, and once mixed, the highest temperature recorded was 26.7 degrees Celsius. The density of the mixture is 1.15 grams per milliliter. We're going to assume the specific heat of water, or the solution, is still 4.184. We want to know what delta H of the reaction is. Again, our delta H of our reaction is going to be equal to Q of the reaction divided by moles of the reaction. Now, we also know that we can calculate Q of quote unquote the solution, right? In this case, because it's not just water in there, there's a lot of other stuff in the solution. Perchloric acid, sodium hydroxide, the products of the reaction. So we're going to calculate Q of the solution, and we know it's going to be equal to negative Q of the reaction, because whatever energy the system gained, the solution gained, that was gained from the reaction occurring. So I know that we have 25.50 milliliters mixed with 25.00 milliliters. This gives me 50 milliliters of solution. Now I need to know what the density, we have the density, and I need to know the grams of that solution. So for instance, I know 50.00 milliliters times 1.15 grams per milliliter. Milliliters are going to cancel, and I'm going to be left with the mass of my solution. This gives me 57.50 grams of solution, and I need this to calculate Q of the solution. Now I know that Q is of my solution or mixture, whatever you want to call it, is equal to 57.50 grams times 4.184 joules grams Celsius times delta T. 26.7 degrees Celsius was my final temperature. My initial was 23.5 degrees Celsius. And so if we calculate this all out, we get 769.9 joules of energy. Now, this tells me then that Q of my reaction must be equal to negative 769.9 joules. And so now I have my first value that I needed in my delta H equation, right? I need the numerator. Now the denominator we got to calculate using stoichiometry. right, we know how many moles of the HClO4 we added to the reaction, and we know since the NaOH solution was highly concentrated, that basically is a fancy way of saying, hey, your NaOH is in excess, HClO4 perchloric acid is our limiting reactant. So I need to figure out how many moles of HClO4 were present, and I need to write out the balanced chemical equation. I know that the balanced chemical equation of this reaction looks like this. Oh, it's supposed to be an L. Plus NaClO4, and that's in the aqueous physical state. It's balanced. It's a 1-to-1 mole ratio. So I need to figure out how many moles of perchloric acid there are, right? And that's going to be 25.00 milliliters of perchloric acid was used. We need to convert that from milliliters to liters, and then I need to multiply by my concentration of perchloric acid, which we know is 0.5 moles of HClO4 per 1 liter of that solution. Then I want to go from 1 mole of HClO4 to 1 mole of reaction. Now we know that that's per mole of reaction because our reaction only has 1 mole of HClO4 in the balanced chemical equation, so it's a 1-to-1 mole ratio here. And if we look, everything's canceled except the moles of reaction, which is what we need to calculate our delta H. This gives me 0.0125 moles of reaction. Actually, we have another 0 here technically. All right, so now I have the other part, and we can calculate it. Delta H of my reaction is going to be equal to negative 769.9 joules divided by 0.01250 moles. And this gives me, I'm running out of space here a little bit. I'm going to erase some stuff just to kind of make some room here. All right, this gives me negative 61,592 joules. Now, we want it in per mole technically. We want it in kilojoules per mole, so convert that. We get as our final answer, put it in yellow, negative 61.59 kilojoules per mole. Okay, if you have any questions, let me know. As always, you can contact me via email to set up a Zoom meeting or just come to office hours that are regularly scheduled.